Once in space, individual structures and equipment that will make up the space solar power system must be assembled and operated and then repaired. Because these systems would be located in a high orbit, roughly 22,000 miles beyond the International Space Station, astronaut house calls, such as those made to repair and upgrade the Hubble Space Telescope, will be difficult and extremely rare. To meet this challenge, NASA and its team had been developing several highly innovative robotic concepts that could be used for the purpose of assembly, maintenance, and servicing of future space solar power systems. Once launched, these robots would live permanently on the SSP platform. In the following video segments, you'll see some of the clever robot concepts that might someday be launched into space for assembling and maintaining large SSP platforms.
Due to the proposed size and complexity of the space solar-powered satellites, it was previously estimated that it would take hundreds of human astronauts a tremendous amount of time to construct and move the required hardware into geosynchronous orbit. Add to this the risks that the spacewalking astronauts would have to endure, things like ionizing solar flares, other galactic radiation, and the constant barrage of micrometeoroids, and it seemed almost impossible to make the dream of space solar-powered satellites come true. But NASA is well known for turning the impossible into the possible, and the solutions to those problems are closer than most people realize.
We're now reassessing whether or not with today's robotic technology we could fulfill some of those good ideas in a new way. Instead of having to only use crew, we have these new options that we can mix into the assembly team.
New generations of robots, such as Johnson Space Center's Robo-Naut, with its ability to handle extremely intricate and precise tasks, pave the way to the future of robotics.
Because each new creation teaches us more about those fundamental technologies, this pace of evolution continues to accelerate. We can create new and unusual robots for new and unusual tasks much more quickly today than we could even 5 years ago.
Entire new species of robots are being developed, each designed according to its specialized job. NASA intends to continue developing technology that will augment human capabilities to deploy, assemble, maintain, service, and operate large systems such as the space solar-powered satellite. These innovations will not only minimize the human risks of space construction, but will also diminish costs by reducing the number of launches needed to boost the payloads into geosynchronous orbit.
These robots can be working 24 hours a day. They can stay out permanently. They don't have to come back into a spacecraft that's pressurized. And we're not risking their lives. If they're injured, well, we'll feel sad, but we can build new ones. They can keep working, and we will not be risking their lives. The crew can operate them safely from back in their spacecraft or even from on Earth.
Robots of the future will not only be used to build large surface science platforms in space, but also to conduct research and even set up and maintain outposts on distant planets such as Mars or beyond. Whether they are working as assistants to spacewalking astronauts or remotely with human supervision, it's clear that advances in robot technology will allow humans to achieve more in the far reaches of space than ever before.
Although space solar power constellations will be of immense scale, assembly, inspection, and maintenance activities will require intricate operations in restricted and confined spaces, in addition to the manipulation of large components. For these operations, a class of multi-limbed, agile, dexterous robots is envisioned. A first generation of the L.E.M.U.R Excursion Mechanical Utility Rover, or L.E.M.U.R, is equipped with a variety of sensors and interchangeable tools to perform a multiplicity of tasks. Forward-mounted stereo cameras provide visual navigation information and vision-based control of L.E.M.U.R tools. In addition, Paul-mounted optics enable close-up inspection or direct visual servo control of the gripper. A combination of these capabilities facilitates complex operations, such as the removal of a damaged or worn part. Using visual feedback of fiducial markers or cues on the end effector and task board allows precise localization of the arm-mounted driver relative to the fastener head. As task complexity and scale increase, behavior-based software architectures will allow the coordination and cooperation of multiple service robots to achieve required goals of autonomous operation, maintenance, self-support, long life, and high reliability.